Click the bell icon to get latest videos from Ekeeda.
Hello guys, welcome to Ekeeda. Today we will see Laplace transform problem number 6, and in this problem we will see what happens when we apply delayed ramp signal to the input of a circle. So let us see what that problem exactly is. So here you can see I have drawn one circuit with respective parameters and their values, and here V of t is a signal and it is a delayed ramp signal. It is 12 into r of t minus 2. So you need to know what is the Laplace transform of this signal, and you can see the title of this problem itself is input is delayed ramp signal. So first we will find what is the initial condition. Well, as it is not given, we will assume that all initial conditions are 0, and now we will use the KVL equation to write the final equation. But before that, we need to know what is Laplace transform of V of t. So for that, again, I have a formula sheet which I have. So here you can see a signal r of t minus a. This is a delayed ramp signal, and the response is e raised to minus as divided by s square. So accordingly, for this signal, it will have it 12 will be the constant. It will be as it is, and r of t minus 2 will be e raised to minus 2s upon s square. So let's solve this problem. So let's write the conditions for t equal to 0 minus. So at t equal to 0 minus, you can see the initial current across inductor and initial voltage across the capacitor. As you can see, no initial conditions are given, so both are 0. So I have written both to be 0. Then it is all about initial conditions. Then the next step is applying KVL for t greater than 0. And when you see in this circuit, when I apply KVL, this is the voltage source. I am going clockwise as usual. So V of t will be equal to 5 into I plus L di by dt plus 1 by c integration of I dt. And so this is what I have written, 1 by c integration of from 0 to t I dt. And then if I put the element values, I will get equal to and now it's time to apply Laplace transform. So I'll write by Laplace transform. You can see this signal is delayed ramp signal. So we have a formula for it, which already I showed to you. So this is the formula. R of t minus a is e raised to minus as upon s square. So applying Laplace transform will yield well, as there are no initial conditions, it is quite simpler in this case. So let's combine all I of s term, because once we get I of s, we will get I of t. This is 5. Then this is small s. You should not get confused between 5 and s. Well, as you can see, one s will get cancelled. So this is the I of s which I have got, 12 into e raised to minus 2s divided by this whole term, and this s also is there, so we should not forget it. So it is 5s plus s square plus 4 multiplied by this small s. So now we will factorize this. So let's factorize s square plus 5s plus 4. So this comes to be I of s, which is 12 into e raised to minus 2s. Well, what we will do, we will keep this e raised to minus 2s outside, and for the rest of the factor, we will calculate the constants. Now here you can see as the factors of this s square plus 5s plus 4 are nothing but s equal to minus 1 and s equal to minus 4. So let's write it as so you can see the factors of s square plus 5s plus 4 are nothing but s plus 4 into s plus 1, and don't forget this s. So now what we will do, we will use the partial fraction for this factor which is in square bracket. So that I will write separately. And by partial fraction expansions, we'll write that this is as, and now we will solve these constants one by one. Let us say we want to get a. So for that what we will do, we will multiply throughout by s plus 4 because we don't want this s plus 4, and then we will substitute s equal to minus 4. So for a, we'll multiply both sides by s plus 4, and so left hand side will give me, and on the right hand side, and now you can see if I substitute s equal to minus 4, both b and c will become 0. So we'll put s equal to minus 4. So when I put it here, it becomes minus 4 plus 1, that is minus 3, and again s is minus 4, and rest of the constants will become 0. So my a will come out to be 1. By applying the similar process, for example, we have to get b, then we will multiply both sides by s plus 1, and then we will substitute s equal to minus 1. So let's get b. So for b, we will be multiplying both sides by s plus 1. So what I will get, this is the expression. This expression in black bracket is what I am talking about. So multiplying now for b, for getting b, multiplying both sides by s plus 1 will give me on left hand side and now it's quite simple. If you substitute s equal to minus 1, both a and c will become 0 and we will get value of b. We should substitute here also. So here also s is equal to minus 1. Well, a and c both are 0 and we'll get b, and that b will be now minus 4, and for c, we'll multiply both sides by s. The reason is, well, every partial expansion has some different technique. So for this c, we will multiply both sides by s, so this s will get cancelled and this also will get cancelled, and then we will substitute s equal to 0. By putting s equal to 0, a and b will both become 0. So I get c equal to 3. So thus I have got all the constants. So we have got a equal to 1, b equal to minus 4, and c equal to 3, and we will put it in this expansion now. Here we'll put the values of a, b and c. So this is how we have solved the partial fraction, but we are not done yet. The reason is, this was our initial expression, which is e raised to minus 2s into 12 divided by s plus 4 into s plus 1 into s. But if you see, we solved this 12 divided by s plus 4 into s plus 1 into s. So e raised to minus 2s term is missing, and that e raised to minus 2s term, when we take it, it becomes I of s, and we want I of t. So we will need all these terms to get inverse Laplace transform. So we'll write now I of s. So here you can see this was our I of s, which is 12 e raised to minus 2s divided by this term, which was factorized. This term was factorized like this initially, and this s is as it is, this 12 also is as it is, and so now this term on right hand side, which is 1 upon s plus 4 minus 4 upon s plus 1 plus 3 divided by s. So we'll write now I of s, we'll multiply this e raised to minus 2s to this all factors, and now we can take the inverse Laplace transform. For that we will need table. You can see this identity number 9, where if you have e raised to minus as into f of s, this one, ninth one, then it is nothing but unit step signal multiplied by f of t minus a. So here we will multiply this e raised to minus 2s to every term. So this is the Laplace transform pair which we are talking about. So if it is e raised to minus as, here it is e raised to minus 2s everywhere. So this a will become here, it will come here u of t minus a. So if it is e raised to minus 2s, it should be u of t minus 2. So this unit step signal or delayed unit step signal will reflect everywhere. Then it is f of s turns out to be f of t minus a. So inverse Laplace transform gives me of 1 by s plus 4. It is nothing but e raised to minus 4. But here it is delayed signal, so it will be e raised to minus 4 into again t minus 2. So I will just draw the first term, or for the first term I will write it. So this term e raised to minus 2s upon s plus 4 on inverse Laplace transform should give me u of t minus 2 because of this property. This is the Laplace transform. So we have this term on right hand side, so we have to apply inverse Laplace transform. So it is e raised to minus a, it is u of t minus a. So e raised to minus 2s, we have u of t minus 2. And then f of s will give me f of t minus a. Now this f of s is nothing but 1 upon s plus 4. And for 1 upon s plus 4, the inverse Laplace transform will be e raised to minus 4, because we know this. See, 1 upon s plus a, we get e raised to minus at. So 1 upon s plus 4, we should get e raised to minus 4 into t. But because this is a delayed signal, and here you have u of t minus 2. So here we will get, see, it is t minus a. Here also it is t minus, so it will be, again it is t minus 2, it will be also here t minus 2. So here is going to be t minus 2. So this is the inverse Laplace transform of the first term. So similarly, if the second term is on inverse Laplace transform should give us, this will come because of e raised to minus 2s term, and here s plus 1, so e raised to minus 1, and again t minus 2. And the third term is And to see the third term, there is 1 by s only. So first we'll write this 3, where here also not written 4. So this 4 will reflect there. So 3 into e raised to minus 2s means it is going to be u of t minus 2. And also it is 1 by s. Now inverse Laplace transform of 1 by s, you can see here in the original table, is nothing but u of t. But that is to be multiplied by delayed unit step signal. So it is going to be 3 into u of t minus 2. So combining all three, because we have this as I of s, so which I write here, and if I apply inverse Laplace transform to this particular sentence or this particular statement, then I should get here I of t. Then we have got for all individual terms, which is on the next page here. So this is what I just combined all these three terms and written on the right hand side. So that's all about I of t, and that ends our problem, because we'll check again. This was our problem, the delayed ramp signal, and we were supposed to find I of t. V of t was given, and we have got I of t. So that's all. So we'll just make a bracket. So this is I of t that we have got, and that ends our problem. So thanks for watching this video. Please subscribe to Ekeeda. Thank you.